Okay, so we're going to look at the next simplest case. We've looked at monatomic gases with a single atom per particle. So the next simplest case is the diatomic case. So diatomic ideal gas. So this will take up the rest of this week and maybe some of next week as well. Finish this topic. Okay, so diatomic is quite simple. It means in a molecule there are two atoms. So e.g., they can be the same, like oxygen or nitrogen, or they can be different. For example, hydrogen chloride gas has different molecules. Or, for example, nitrous oxide, NO. But what's important is there are two atoms. They can be the same or they can be different, but each molecule has two atoms. That's what's important. Okay. Now these molecules can vibrate and rotate. As well as moving in the normal way. So vibrate looks like this. For example, if I have oxygen. Sorry, then these can move in and out. And they can rotate. So again, if I have oxygen, they can move around like this. And we want to know what these excitations, these possible vibration and rotational excitations, do to the energy and heat capacity and so on of the gas. Now, for the case of vibrations, we've worked out what the energy levels are, and they're labeled by a single number, n. The formula, it was simply, we assumed that they were harmonic oscillators. So then it's the frequency of oscillation times Planck's constant times n plus a half, where n goes from 0 to infinity. So as I said, the method we used before is general. So we start by looking at the energy levels. Then we compute partition function and so on. In this case, you can compute the partition function exactly, in fact. In this case, the energy levels are labeled by two numbers, L and M. And the formula is some constant, which we can describe in terms of a moment of inertia I, like this. The important part for our purposes is the dependence on L and M. It doesn't depend upon M. M is a degeneracy factor. And the energy goes like L times L plus 1. I gave you these results before, I'm just reminding you. And here, let's start by L. Here, L is also a non-negative integer, like this, and M takes values between minus L and L. So an obvious example of this, if L is, say, equal to 3, then M is minus 3, minus 2, minus 1, 0, 1, 2, or 3. So in this case, it has 7 possible values. Okay, so again, we can calculate the partition function. And again, we have to use this approximation we did before because they're indistinguishable. We divide by n factorial. And this implies that we are looking at the partition function at temperatures about greater than a Kelvin again. So this again is the indistinguishable particles term. a particle now, be careful, a particle now refers to a molecule, not to an atom. So one particle is one molecule. So n is the number of molecules, not the number of atoms. Okay, right. Then you have the sum over all possible microstates, or, well, all energy levels, but now there are three sums. There's a sum over the translational part, which depends upon the vector n. Then there's the sum over the rotational part, which depends upon L and M. And then there's the sum over the vibrational part. Well, okay. Unfortunately, I gave it the same letter, which depends upon the scalar n. So this n is not the same as this n. This is a vector n labeling the translational kinetic energy, and this is a scalar n labeling the vibrational energy. So this is a sum over all possible states. It has a translational energy state, a rotational energy state, and a vibrational energy state. So it can do all three things together, right? It can move and rotate and vibrate all at the same time. And then the total energy of the particle is the sum of all of the energies. So I have e to the minus the translational part, that's epsilon n, then the rotational part, that's epsilon Lm, then the vibrational part, that's epsilon scalar n, all divided by kBt, and taken to the number of particles. So I've just put all these things together. Before, it was just this single sum over vector n, and the energy only depended upon the vector n. Now I've added in the rotational energies and the vibrational energies as well, in these last two terms. But you see that I can separate these sums again. The sum over n, vector n, only enters in the first term. The sum over L and M only enters in the second term. The sum upon scalar n only enters in the last term. So I can split this as three sums. The first is the translational part. The next is the rotational part. I should probably write bigger, otherwise you won't be able to read it. Right? And then finally, we can write the vibrational part. Like this. So it's a product of three terms. The first term is exactly what we found for the monatomic gas. This term is exactly the same as for the monatomic gas. This term is only involving the rotational parts. This term is only involving the vibrational parts. So the partition function splits as a product of three terms. This first one I can call Z trans. Let me just call it ZT to keep things simple. Big T could be temperature, so I'll call it little t. T for translation. So this first term is the same as the monatomic gas. This next term, okay, and it depends upon both the temperature and the volume of the gas. This next term is the rotational part, so I'll call this ZR for rotation. This only depends upon the temperature. And this final part is the vibrational part, so I'll call it ZV, and again, it only depends upon the temperature. So therefore, the partition function for the whole gas splits as a product of three partition functions. The first for the translational part, which is the same as for monatomic. The next for the rotational part. The next for the vibrational part. This is important because it splits like this. This means that you can treat the translational, rotational, and vibrational parts separately. So on Thursday's class, we're going to consider only the rotational part. And then next week, we're going to consider only the vibrational part. So the fact that the partition function factorizes like this allows us to consider each kind of energy separately. Each degree of freedom we consider separately. Okay. So for example, F, T and V, this is defined as minus kBt times the log of z. Now if I take the log, then the product becomes a sum. Okay? So this is minus kBt let me write it in shorthand. Minus kBt log of 1 over n factorial times zt times zr times zv minus kBt. The first term I can use the Stirling approximation, so this is n, 1 minus log n. Then this is the sum. The first term I can use the Stirling approximation, the minus and the log, just give me log of n factorial, so this is n kBt log n minus 1. That's from this. And then the last terms are just log of this, log of this, log of this. So this also splits into a sum of translational, rotational, and vibrational parts. Okay? So the fact that the partition function is a product means that in the free energy I can just add the free energies together. So I can add the free energies together. And similarly, the total energy in the gas is equal to the sum of the energy in the translational part plus the energy in the rotational part plus the energy in the vibrational part, and so on. So the partition function is a product of partition functions, and energies and heat capacities and so on, we can add up the contributions separately. So we've already calculated the internal energy of the translational part. Okay. We know that this one is just 3/2 kBt, n kBt. So now we can calculate these ones separately as well. And what we'll do for the next couple of classes is calculate what's u for the rotational part and what's v for the rotational part.